So we are looking at this equation reaction where we are having a system of hydrogen and oxygen atoms where we have NH, capital NH number of atoms of hydrogen, capital NO atoms of oxygen, and they react, and then we are considering 6 products. Okay, so we could consider a few more products, and then the system is going to get a little bit more complicated correspondingly, and the temperature is going to change, the final answer is going to change correspondingly. So the accuracy to which you want the temperature depends on how much you want to go through the calculations, and therefore you decide on the number of products you want to take, right. So what we already saw is these are the atom conservation equations, right, and then these are the hypothetical formation equilibria equations, or they are coming from there. So in the last class we wrote actually these expressions for this KPFO, KPFH, etc. We have now rearranged in such a way that we will now get expressions for NO, NH, NOH and NH2O, each of them in terms of NO2 and NH2. Okay, so effectively we are now recasting everything that is there in the products in terms of only the reference elements. Okay, so the reference elements really is the key. So once you do this, you now plug these back in the atom conservation equations, right, and what are you going to get? So you get 2 Kp FH2O NO to the half NH2 N over P to the minus half, that is for here, plus Kp FOH NO2 to the half and H2 to the half, plus KPFH, that is for this, sorry, yeah, NH2 is already there, I am going to write this towards the end. So KPFH NH2 to the half N over P to the half plus 2 NH2 equal to capital NH, right, running out of space there. So I am going to write the next equation here, which is not very different now, so, or difficult now. So KPFH2O NO2 to the half NH2 N over P to the minus half, plus for the OH we have KPF OH NO2 to the half and H2 to the half. We do not have a N over P for this, yes, plus then we write for NO and then we put the NO2 later on. So we can now write this as KPF O, it's here, so NO2 to the half N over P to the half plus 2 NO2 equals capital NO, right. So what we have now is we actually have 2 equations, okay, 2 equations, and explicitly speaking 2 unknowns, the 2 unknowns being NH2 and NO2, but implicitly we have a N sitting here in a couple of places, and that is a villain, it contains all the unknowns, right. So it's like you've really not eliminated more unknowns than we want, therefore all the unknowns are there, so we have to do this iteratively, okay. So these are two equations and two explicit unknowns NH2 and NO2, but also contain N which has all the unknowns. So which means we adopt an iterative solution procedure, right. So this is a bit of a cumbersome process. If you are sitting in an exam, you hope that you don't get a question on even one iteration to be manually calculated, because it's a little bit of a nightmare. So the first thing you have to do is do a initial guess for the N, okay. So assume an initial guess for N based on stable products, okay. Stable products. So we now have NH2 plus half NO2 gives half NH2O plus half NO minus 1/4 NH times O2 if O2 is in excess, right. So if how much excess, we can actually quantify this. If half NO is greater than 1/4 NH, then initial guess for N equal to, simply we are essentially looking at this plus this, okay. So these are the final stable products to expect. That means we disregard all the unstable products, right, and therefore we can expect this to be half NH plus half NO minus 1/4 NH, and that would be 1/4 N sub H plus 1/2 N sub O, yeah, for this case. This is like a fuel lean situation, and or half NH plus I'm sorry, half NH H2 plus half NO O2 gives NO amount of H2O. This is actually doing an algebraic balancing, okay. So it's sort of like interesting. Instead of a high school way of numerically balancing, you do an algebraic balancing, right. So half NH minus NO times H2, where H2 is now the excess species. If half NH is greater than NO, this is the same as saying if 1/4 NH was greater than 1/2 NO, okay. We were comparing halves and quarters there, so if you want to do the same thing, you can do that. This is fuel rich. This implies initial guess N. Just add up these numbers. So NO plus half NH minus NO is simply 1/2 NH, right. So you can start with this initial guess for N, and then you have to proceed. The other problem we see is these are actually functions of temperature, okay, these and so on, right, and that is the temperature we are trying to find out, okay. So we do not know what the temperature is, but we need to take values for these, so that is like a big problem, that is a huge loop, okay. So what we have to do here is there are like about 2 or 3 loops that we have to think of. We also are better off with actually so doing this we do not know the KPFs because T adiabatic is unknown. These are all evaluated at T adiabatic. In fact, I should specifically say over here right. So therefore outer loop, outer iteration loop would be to start assume T ad, okay. So you have to make an assumption, you start with some guess value for the T ad, and so and then so the algorithm is now guess T ad to guess n 3 calculate ni double prime 4 calculate T ad, okay, by comparing with RHS of adiabatic flame temperature equation, which is essentially the enthalpy balance equation, and then you go around, right. Of course you can actually check here, I'm sorry, between here and here you can check satisfaction of state equation, or you can say equation of state, right. So equation of state is essentially if you now have something like PV equals n or T ad. So for the assumed T adiabatic, okay, if you have now converged on ni double prime, okay, then you should now get an n that's different from the guess value, okay, and that final n that you get should satisfy this, okay. So that's something that we have not quite used up, and therefore you can use this to check, and then you go through this loop, right. Now it's easier said than done, because solving this set of equations here is actually pretty nightmarish, okay. We are looking at a highly nonlinear equation, so you are looking at products of unknowns and powers of unknowns that are non-unity. So this is not very easy to solve, so this is pretty difficult to do to begin with, and the more the number of products that you assume, the more difficult these equations are going to get, the more the number of atom types, okay. You will now have more atom conservation equations, and finally you will have in fact if you have more atom types you will have more products to consider, alright, the first place. So the hypothetical formation equilibria equations will flare up to as many products you have assumed, and you have to now rewrite them and plug them back to as many atom conservation equations as you have the number of atom types. So all these things will become much bigger, and so it's very difficult to do this. So for example, for a carbon, hydrogen, oxygen, nitrogen system, right, we could assume the products as CO, CO2, carbon in gaseous form at these temperatures, okay, H2, O2, OH, NO, H, N2, NO, H2O, etc. Right, and so then you have to so there are some initial guesses that we can also think about. So for C, NC, H, NH, O, NO, N, NH system, right. So that means you have a system by which you have NC number of carbon atoms, NH number of hydrogen atoms, and so on. So that means both the reactants are included. Like if you have oxygen there, so oxygen could be figuring out in the hydrocarbon or oxygen separately or both, okay, everything put together. So this could be like, if you now consider only the stable products among these, look at how many products we have considered, like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 already. Yeah, or did I miss anything? H2, O2, OH, N, OH, N2, NO, H2O. Yeah, of course, I knew I was missing this. We have to assume carbon solid as well, because that's actually the reference element for carbon gas. Without that, you're going to get stuck, right? So that's about 13 species. Let me tell you that 13 species is actually not a very high number in reality. Okay, so this is an easy problem. Okay, so okay, we're looking at what could be a good initial guess, right? So if you now assume that your stable products are let's say carbon dioxide, water, and let's say nitrogen, and of course if it's a fuel lean situation, you should get some oxygen out. If it's a fuel rich situation, you might want to get some hydrogen out. So I just put a reverse tick to indicate that you will have one of these, right. So if you now do this algebraic balancing, you can get something like H2O plus half NN N2 plus half NO minus NC minus 1/4 NH O2, okay, if half NO is greater than NC plus 1/4 NH. So it's kind of like this is the combination of the hydrocarbon for which you need to have so much oxygen in excess for a fuel lean combination to assume O2 as a final stable product, right. So this is a fuel lean situation. For or okay, I'll just start with this right there and then say this could be NCCO2 plus NO minus 2 NC H2O plus half NN N2, that doesn't change, and plus half NH minus NO minus 2 NC H2, right. This is if half NH is greater than NO minus 2 NC, which is supposed to be, but NO is much greater than, so not greater than or equal to 2 NC, right. So we want to have this combination, and then this should be less than the half NH. This is the fuel rich situation. So if you do this, then you can now get your initial guess for the N, because all you have to do in the fuel lean case is to add NH plus half NH, NC plus half NH plus half NN plus this thing, and maybe cancel something, and you now get the total N as the initial guess. Okay, the number of moles is not the same. Okay, so we are now basically looking at a initial guess for the total number of moles of the products based on the stable products. Effectively what we are saying is we should expect these things, that is, sorry, the NH, NO, NOH, etc. to be in small quantities. We expect largely the stable products, but the other ones are going to be in small quantities. Higher the temperature, more these will be. Okay, and then they will try to bring down the temperature. Okay, so there is an equilibrium that gets attained by having more of these and getting the temperature down. Okay, so that's the reason why we are actually starting with an initial guess based on the stable products composition. Okay, so if it's a fuel rich situation, you can add up these in order to get your initial guess for the total number of N. Alright, now the point is, do we actually have to go through this Herculean task? You try to do a computer code on this, it would be a fairly good assignment for a course. Okay, so, and many times many students who are not spending enough time on this don't succeed. Okay. So how in the world that people can find the adiabatic flame temperature realistically when it's going to be a Herculean task to write a code to do these things? So the answer is there are codes available. Okay, so most of the time we don't have to sit and do these calculations all the time. We use some standard codes that are available. So one of the most popular codes is standard computer codes are available as open source. Okay, well, when I say open source, I typically bother only about getting the executable version, don't worry about the source code itself. So the most popular one, to the extent I know, is the CEA2. That's a current version of what's called the CEA. The CEA came out in 1996. The precursor to that was the CEC71, which came up in 1971, and it was published in this the CEC71 was published in this special publication called NASA SP 273. So many times people refer to NASA SP 273 calculations. So essentially they are talking about a latest derivative of this, which is the CEA2. Okay, so it's actually available in the NASA Lewis Research Center code. So you can look for these and download and so on. I can give you more information about this. There is also another one we can look at called StanJan and so on. So there are actually many more codes than this. Okay, available. You can look up, but effectively, in fact, I want to point out one thing about CEA2. It not only gives you things like the adiabatic flame temperature, it also gives you other things like for example transport properties of the product mixture. So if you now have a product mixture, you can also calculate, of course typically you are expected to obtain molecular weight of the mixture, for example the ratio of specific heats for the mixture, but what more this can do is to also get you thermal conductivity and viscosity, those kinds of information also. So it's extremely useful to have this code up and running for most applications that you want to do. You get into doing some engine calculations or rocket calculations, this is almost like the starting point. Okay, you have to have this with you for you to be able to do anything more. So what I will do later on is to put out some sample calculations in the website into which this video will be uploaded, so that we can go through numbers on like let's say you now throw in some CP data like polynomial fits or something like that, or make an assumption on calorically perfect gas and say constant CP, but you need to look at typical numbers for these and so on. So we can do this, and in fact I can also show you if you assume only the standard products, like let's say if you now take methane plus oxygen and give you carbon dioxide and water, we can go through that calculation and you will find that the temperature is actually shooting up beyond about 3000 Kelvin. But if you now add some more and then let's say you run a CEA2 kind of thing, you now have a huge list of species that you have assumed for the products. You will find what the temperature is for the same composition of methane and air that you considered and so on. Well, so we can I'll put out those kinds of exercises in the website as we go along, which you can look at, but we have spent a little bit more time than intended on the adiabatic flame temperature calculation. Finally, before I close this module, I think I should mention something very basic. Okay, so one is this is the definition of what's called as equivalence ratio. We didn't quite get an opportunity to talk about this because we first talked about what's called as a stoichiometric ratio, but then we were diverted at the time by what's meant by heats of formation of the products. Okay, because the definition of the stoichiometric ratio involved that we have to actually get the most stable products which have the most negative heats of formation, standard heats of formation, and then we were diverted into that. And that was right, that is quite correct. So to have that happen, so we have to now get the jargon right. So when you now talk to the industry people, they keep talking about something called the equivalence ratio. Okay, so the equivalence ratio is typically given the symbol phi, and this is defined as the fuel air ratio for a given condition. So this is given by fuel air ratio at stoichiometric proportions. So in other words, you don't really worry about exactly what the stoichiometric fuel air ratio is. Okay, and of course you can also think about what if air is not the oxidizer. Okay, and not all of air is oxidizer, only the oxygen part of it is typically the oxidizer. The nitrogen is like an inert. Doesn't matter, you can look at a fuel oxidizer ratio or fuel air ratio. Okay, and you now form a equivalence ratio that is like this, which means phi equals 1 is stoichiometric and phi less than 1 is fuel lean, and phi greater than 1 is fuel rich. Okay, now the rocket people like to operate fuel rich, whereas the air breathing engines people like to operate fuel lean. Okay, so the rocket people don't really talk about a fuel air ratio, they talk about an oxidizer fuel ratio. Alright, so when you talk about an oxidizer fuel ratio, you could write this as oxidizer fuel stoichiometric divided by oxidizer fuel given. So you now invert this because you have inverted your numerator and denominator, so that this holds. you always have, this is something that I used to get confused as a student, okay. Do I define it this way or do I define it that way, or which way should be it, how do I invert and all that stuff. Don't think about all those things. What matters finally is this: if your phi is less than 1, it's fuel lean. You have to define your phi like that, okay. That's how it works. And phi greater than 1 should be fuel rich. This is like the mantra all over the world on this, okay. So you don't have to think about this at all. Then you work out all the other details, okay. Then I also want to emphasize these are mass ratios. They are not the number of moles or molecular weight, nothing, again nothing like that. It's actually the mass, okay. And many times in flow situations you could also use mass flow rates, m dots. So you can say m dot f divided by m dot a divided by m dot f divided by m dot a stoichiometric, all right. All those things are permissible, but it's all mass ratios, okay. Fine. So with this I should stop this particular module, and let me now get into the next topic, which is chemical kinetics. Right. So let's now define some. So keep in mind that we are still in the preliminaries, okay. We have not got into combustion yet, okay. So we have to learn. I told you we needed to learn some thermodynamics, we needed to learn some chemical kinetics, some amount of mass transfer leading up to Fick's law, and then we will get into some conservation equations derivation. That's when we are actually getting into combustion. At the moment not yet, but we need these preliminaries. So some definitions first. Some definitions first is one, a mass concentration of species I, okay. What's mass concentration? What is meant by mass concentration? Mass concentration, what does it mean? In what way? We are looking at mass, right? So mass of that species in the total mixture, in what of the total mixture? Is it the mass of the total mixture?
Mass of the total mixture.
Sorry, that's the next. Okay, so you're looking at mass concentration. So what would concentration really mean? Huh? Based on volume. So you want to say you now pick a unit volume of your species, of your mixture, okay, and then you now look at what's the mass that's contained of a particular species in that mixture. All right. So what is this? Mass per unit volume? Density. Okay, so this is something that we actually know. Right. So this is basically this is given a symbol rho I, which is the density. Okay, this is equal to mass of species I in volume of the mixture, right. I am writing this in a congested manner because we are supposed to know this. Okay, so shouldn't have to worry about this, or maybe put the equal to sign somewhere here, and then B, because most of chemistry is done in moles, okay, so we also have now molar concentration of species I, which is given a symbol Ci, C sub I, right. Now this is pretty easy game, Okay, so what do we know for Ci? How do you define this? Not yet, huh? So this is basically number of moles of species I per unit volume. So number of pi I per unit volume of the mixture, right? Okay. Now I want to actually get the mixture density. What do I do? Do I take an average of all the species densities, rho I? Can we think about this? Not yet. Yeah. We want to know the mixture density. So what's the mixture density? Okay, you take a unit volume of the mixture. As we speak, there is air around, which is a mixture. Okay, so I'll take a unit volume of the mixture and then find out what is its mass. Okay, but we know that it is actually composed of many species, and each of those species has a mass rho I per in that volume, because we are now saying unit volume, right? So if I want to know the total mass of all the species in that unit volume, I simply have to add all the masses of the individual species, with the denominator being the same, that is the volume. Okay, so if I now split up the denominator for each of those, I simply get back the sum of all the densities of individual species as the density of the mixture, right? So density of the mixture rho, right, is equal to sigma I equals 1 to n rho I. Just have to add, don't do any averaging or anything like that. Alright, so just add all the densities to get the density of the mixture. And similarly, molar concentration of the mixture, C is, you just have to add the total number of moles that is there per unit volume, right? So total number of moles is like number of moles of this species plus number of moles of that species and so on in this volume. Therefore this is simply going to work out to I equals 1 to n Ci. That's it. Okay. And what's the relationship between Ci and rho I? One of them is number of moles, okay, per unit volume, and the other one is mass per the same unit volume. So the volume is pretty much the same for both. So the only difference between them is, on the one hand you are counting the number of moles, the other one you are counting the mass. So what's the difference between the number of moles and the mass? What's the factor that differs? Sorry, the molecular weight. Yeah. So the molecular weight basically tells you what is the mass per 1 mole, right? Therefore if you have so many number of moles, you need to have so much more mass as the molecular weight. Therefore the relationship is Ci equals rho I divided by Wi. Okay. Now these are things that are kind of confusing to begin with. If you are not used to, there's a reason why I am going through these things rather slowly. Okay, so this is where we now say capital Wi is the molecular weight of species I, right? The second definition that we want to have, and I'll try to use the next panel, 2a is mass fraction. Mass fraction, and we use the symbol mass fraction of species I. Species I, we use the symbol Yi. What do you think is mass fraction? Now this is pretty indicative. Okay, you can guess these things, right? So mass fraction is mass of species I divided by the total mass of the mixture, right. So of course you are not going to take like the mass of species I in this entire room and then divide by the total mass of the species, all the species in this entire room. You could now basically think, I will take a unit volume of the mixture, look at how much mass I have of species I, look at how much mass I have for the mixture in this unit volume. So per unit volume basis, which should work just as well. Okay, therefore we could say this is rho I divided by rho. All right. Now, if you now are looking at the contribution of the ith species mass per unit volume to the total mass per unit volume of the mixture, then if I add up all of these mass fractions, what should I get? 1. Good. So this implies that sigma I equals 1 to n yi equal to 1, and this is going to actually come in pretty handy to us later on, because pretty soon, okay, coming next week, we will have lots of very dirty looking partial differential equations to stare at, and one set of, and then you will have sets of unknowns. It's not just unknowns, it's like sets of unknowns. Okay, so we'll now look at one equation and say that's actually going from I equals 1 to n, therefore there are n equations and there are 3n unknowns and so on. Okay, so let's be looking at n, and n is actually not too small. Okay, so and we will talk about this. Okay, so n could be of the order of like, let's say 10 or 100. Okay, let's say 10 to 100. Okay, to be very modest. So you're now beginning to look at something somewhere between about 50 equations, 500 equations, and all those things. Like just write them. So yi is going to be one set of unknowns, right? So in all these things, sigma I equals 1 to n yi equal to 1 is going to now come to us like a big relief, because it's a simple, nice algebraic equation, good old middle school days, not even high school days. Okay, so just deal with algebraic equations, it's great. Yeah, so this is going to be one of the equations that we will actively consider among this dirty set of equations later on. So similarly, for B, we could now say mole fraction of species I. Okay, so the only thing that we are doing now is we know the trick, what we want to do, right? So the only thing that we are doing now is to introduce the standard notation. Okay, so it's given as xi, and as a matter of fact we introduced x as a mole fraction last class, right, when we were looking at the how to relate the partial pressures to the total pressure. So xi is, what do you guess for this? Ci divided by c. Okay, no big prizes for this guess, huh? We're getting there. So therefore here again we can say sigma I equals 1 to n capital Xi equal to 1, right? One more, and then what's the relationship? Relationship is the Xi equal to yi divided by wi divided by sigma I equals 1 to n yi divided by wi. All right. So this is the relationship between x and y, and this is also pretty important, as we will see later on. There are these mass transfer equations and chemical kinetic equations that are based on molar concentrations and mole fractions, whereas when we try to do mass conservation, we are more interested in mass concentration, namely density, and mass fractions. All right. So on the one hand, for the fluid dynamic kind of equations, conservation equations of mass, momentum, energy, we will be dealing with mass or a mass basis, whereas for the chemistry and so on, we will be dealing with the molar basis, and there this set of equations, that is relating the mole fractions to the mass fractions, is going to come in handy. okay, we need to have these set of equations. In fact, what will happen is, and I tell you this, you have to recollect this, and I again come back to this, we will have to treat both xi's and yi's as unknowns, okay. So one set of equations that will link the two is this equation, this set of equations. This is actually valid for every species in the mixture, right. So we will have this relationship also come up in a big way. Alright, so with these definitions we can now get into some kinetics, and right now what I am going to do is to only bring in some notation, okay. So we now talk about what's called the law of mass action, right, and the axiom that you're working with is atoms and molecules cannot react unless they collide, okay. There are exceptions to this, okay. There are exceptions, like for example you can heat a molecule and then it starts vibrating and dissociating and so on, so it does not really collide with any other molecule. It can also be photosensitive, that means like light radiation or electromagnetic radiation can create these kinds of vibrations and stuff. So there are exceptions, but at the moment let us not worry about this, and we have to start with this axiom. Now strictly speaking we need to actually get into the details of this axiom, as in how the collisions happen and so on, only when you are getting down to something like a kinetic theory level, okay, or kinetic theory of gases level, or even further if you want to get into something like quantum statistical mechanics. So if you have to now work out the collisions, how they happen, and what is the statistics of these collisions, and how the energy exchange happens and all those things. We won't do any of those things here, thankfully, right. I just tried to scare you there, okay. What we are going to do is to adopt a continuum approach. So in a continuum approach what you essentially mean is, at a particular point in the flow field you have a nicely defined density, concentration, mole fraction, mass fraction, all these things. How you got that is not your problem, okay. It's there, again you can assume that it is there. So with this we will actually be looking for laws that are just taken for granted at the continuum level rather than derived from molecular level. So the thing that we were basically looking at is, let's start with an example. Example is, let's suppose that you now have H2 plus half O2 gives H2O. Here with this we can write a change in the number of moles of H2, okay, and then we divide this by -1 to indicate that this change is in the manner of depleting this this number, and similarly we now write this as change in the number of moles of O2 divided by -half to indicate that you have a half a mole that goes for every 1 mole of hydrogen, and it goes, therefore you have negative, okay. So this negative indicates depletion, and the half or the 1 indicates the coefficient there, and that's equal to 1 for every mole of hydrogen that is produced you have plus 1 mole of hydrogen water that's produced, right. So this is actually 3 equations, yeah. So you can now look at, this is one equation, this is another equation, and these two together is another equation. Each of these 3 equations effectively relates what should be the change in the number of moles of hydrogen for a corresponding change in the number of moles of oxygen, and so on, okay. And the signs effectively tell you whether they are getting depleted versus getting produced, okay. So if you can write this like this, then in general we can write dN1 divided by nu I double prime minus nu I single prime plus equal to dn2 divided by sorry nu1 nu2 double prime minus nu2 single prime, etc. That is like you can write dni nu I double prime minus nu I single prime, where we had this notation or we can say sigma I equals 1 to n nu I single prime mi gives sigma I equals 1 to n nu I double prime mi. So this is like a generalization of what we just went through, and let's now call this d psi, where psi is what's called as the degree of advancement of the reaction. Let me stop here for the day.